working from the lakeside these first 3 days of this week, which is great. Bartolino, the aficionados will remember the episode from Bartolino. So the season has opened. I grilled. That was awesome.
Yeah.
What's up with you, Thomas?
Yeah, we had barbecue too, like on Wednesday, and yeah. Other than that, it's been the summers here.
Yeah.
We've been to the swimming pool a bit, but
Yeah.
lots of work too.
Yes. About that, we felt we always iterated on the same models, like when and stuff. And so we started wondering, or not just us, but in general, what models can I apply Thunder to, and what models are supported out of the box. And we know what the largest collection of models out there is, which is Hugging Face transformers. And so we made a list. We borrowed the list of models from our colleagues at NVIDIA. Then we looked at the models that are in VLLM, supported in VLLM, and the models supported in SGLang. We compiled a unique list out of those, and it's about 200 models, more or less. And then we threw Thunder at it. Of course, it wasn't that simple, in the sense that there were paper cuts and stuff. Thomas had to work his magic. But now we have some numbers. So, and what was tested was, can we run the JIT on them? And so now we're automating the process of checking. So we'll make a PR where we can run this in CI periodically and track coverage, which is great. But let's take a look maybe at what we support and what we don't support, and then we'll drill down on a particular class of models we don't support yet, because they have data-dependent control flow. Maybe some of you already guessed what they are, but let's get there in stages.
Yeah. So do we want numbers?
Yeah, so why don't you show the screen and take a look at how to test something like that.
Yeah, it's all very raw. So I got this script from Luca, actually. And so what we do is we try models and we run through a list. And then we have a fairly large list. And I can show this too, if I find it. And so we have here the list of all these models. And you see it's a lot of them, right?
Yeah.
That's the main property. There are really, really many.
Yeah. And also one thing that's worth saying, superficially, they're all transformers. But they're written very differently. Some implementations are weird, some are less weird. And they're not all the same. Like, they have different properties, different ways of handling their layers. So there's a good variety.
Right.
Some ops here and there. Maybe let's also take a look at the at what we do to run them, to just run the interpreter on them.
So we run the JIT on it, and we added a few locusides here because there was like a bit of weirdness. For example, we want to run this, and I'm running this now on an H100 because some of the models wanted flash attention, and you can't install flash attention without the GPU. But so we had a new magic lookaside for a very curious PyTorch thing. So Hugging Face transformers, from back when you did that, they use a lot of automatic multiple precision things. And so they have some regions where they want to disable it. And you can call with auto AMP, torch AMP, with the context manager enabled false. But if you do that and the device is the meta device that you do it on, then it hits some weird bug. And the first thing was there was a bug in Thunder with the Python version we're using here, 3.10, which does exceptions totally different than the later versions of Python. And there was a bug in the exception handling that caused part of the traceback to not appear properly. And so we needed to fix that. And then we saw where the error came from. And then we added a little look aside because here for the tracing properties, we don't care about the automatic multiple precision being disabled somewhere. And so this was a small thing that we did. And then we ran the JIT, and then we just tried to run the prolog. And this goes through this function, and this exposes some of the internals of Thunder, where we first set up some information, the compile data, where we get the traces, or no, they're not the traces, they're from the compiled stats. And then we get some cache info, which captures the state of PyTorch, like all the context managers you might have started, and whether you're in grab mode and stuff like that. And then we acquire the initial trace, and this will run the Python interpreter, the Thunder Python interpreter. And then we apply some transforms and build the cache entry, and we run the prolog. And so this is the first step that happens when you run the model in Thunder. And then you would obviously run the compute function.
Yeah.
But so we do this here, and if it works, we claim success, which doesn't mean we ran the model, but we're on the meta device, so we have a first indication. Or we may hit failure. And there's the thing, if we can't like set up the model for tracing, then we skip it. And there's some 30 models of these 250 or so that don't work out of the box because they use old code, or some of them seem to have disappeared from Hugging Face in the meantime after compiling the list. And so there's some things. And so we write this into a file, one for each model. And so we have all these. And now we need to kind of try to drill down. And so the first thing is we want to have some sort of pass rate. And if we grab for success, we see that we have 169 files that succeed, or maybe we just do it like this. There we see we have like 160 that succeed, there's 60 some that fail, and there's a few 30 or so that we skip. Yeah, that's the score. And then we need to drill down, like find out why things don't work. And so if we check, like maybe here the bottommost, the bottommost is a success one. So it used to fail, but we fixed some things already. So let's look at ExcelNet data, ExcelNet. And so this has one thing is on Meta and the other is on the CPU. That might even be something.
Maybe a buffer.
It probably is something where the model creates a new tensor.
Yeah, on a default device.
On CPU on the default device, whatever.
Yeah.
And then we try to multiply it with something or add.
This might be quite easy to fix, actually.
Yeah. Some of them will be easy, but so to have some sort of overview, you can also, like, I have all these clumsy grep commands. So I do the following. I try to get all the failing things, and I get a list of file names from this. I sort that for no particular reason. And then I pass it to tail. So I get the last line of each file, and I sort that, and then I call unique on it. And then with counting, and then I sort by the numbers. So the most important ones are last. And so we used to have like different ones, but now we have an overview. Here, this is actually where the error message contains a blank line at the bottom. And it is one of our own, sadly, that is a bit verbose, but it's about not implemented operators. But so the other things you can go through, and then you have a sort of a quantitative view, like there were 16 models that tried to cast a tensor to a Boolean, and or yeah, and that's not supported. And some of those were for some training dropout, and so we tried these models in eval mode first. Yeah, and for some other things, we had some models like to pass the values, tensor values, to the full function, which only takes usually it takes a number, which it creates a tensor filled with that number. But you can actually invoke it, or you can actually pass a tensor. But that is a bit tricky, because if you do it in eager mode, the tensor will be converted to a number, and it will be on the CPU too, regardless of what you do next.
Synchronization point.
Yeah, so it's a synchronization point. And also in Thunder, this would be like tricky, because when we cast things to a number, then we have the problem that we want to hard code all our numbers, and we don't want to do that here necessarily. But so we could extend full in Thunder to just cover that case as well, because there were like a double digit number of models doing it. Whether I recommend that or not, maybe not as much as it's used. And so the remaining things, there are a number of things that are more or less easy or hard to support. So some things will be like, here's a not implemented error: repeat interleave does not support a dimension argument yet. That's certainly true, and of course we could implement that if we want to have
no hanging fruit. Exactly. Whoever wants to tackle this, exactly. Yeah. But it's a work of like, it's a long tail, right? So everything is kind of workable, except a few things that we'll see in a few minutes that require some more work.
Right. And so
and as part of this, we also implemented advanced indexing, which is super awesome.
Yeah, and that is the only thing that is not in main yet. Because so obviously many people noticed, and then one PR got stuck, and then I tried to understand what was going on, and I didn't. I implemented a new version of it, which is kind of a sad thing to do. But yeah, what can you do? But so there's a remaining few, and you see here, PyTorch.where does not support specifying only a condition in Thunder. And so this is one of the things we currently kind of struggle with: functions that return variable size tensors. And because that is one of the ways how you get into data dependent control flow. For example, then the next thing will be that you kind of iterate over something there. And so this is all a bit tricky. And so this is a thing: casting a tensor proxy to a Python float is not supported. This is for similar reasons. But the torch.where, and then there's a non-zero here. So the non-zero has the same issue.
Yeah.
we try to auto-register functions that we don't have, but in this case, this is tricky because of the output shape. And so I think there was a third one that is similar. Yeah, the Boolean advanced indexing, that also, like, you take all the elements that are non-zero. It's a bit equivalent to the non-zero. And so those are tricky ones, but they are also immensely popular ones. And now,
oh yeah. So let's look at the list. So first point of the episode is, yes, we support a ton of models, and the JIT is actually able to run through some very weird code that is contained in some of those models. So it's really coming of age, and sometimes it takes a fairly concentrated effort, which is what happened this week, to unblock a bunch of them, and it's good, and we'll keep monitoring them. But one that we knew, one category of models that is fairly popular that we knew was going to pass, we're not going to pass, is the MOEs. So MOE started all the way back when were popularized, when I think the first really popular one was Mixtral a couple of years ago, or maybe 1 year ago, and it's just time flies. But since then we had a bunch of them, DeepSeek, R1. Yep.
One would have to say that similar concepts, of course, were there before, right?
Oh yeah, no, for sure.
All sorts of things, like ensembling was like the most trivial mixture of experts, where
yeah, for sure,
applied equal weight, and there was also this committee of expert things in the stuff. But yeah, so it became really popular with Mixtral or so. Or some time around that time, right?
Yeah, exactly, because it showed that you can scale parameter count without having to scale flops, and because you select, basically what mixture of expert is a model. You can make it up in different ways, but in the LLM world, is basically you have a single attention, but when it comes to the MLPs, the blocks that do the MLP layers, what you do instead of having just one giant MLP is you have multiple of them, and then you have a router at before the MLPs that decide which one of the MLPs will be activated. And there are many variations of it. Sometimes you just select a fixed number. Sometimes you keep one shared, and then you pick others that come and go. So there's a few of them that always stay in the mix, and some of them are picked. So there are many ways. One thing that it's important to understand is that the MOE layers are one every block. So every MLP is basically a zipper, where you come together at the attention, and then you fork off to multiple experts, and then you come together at the attention, and so on. And so you have this interleaving pattern throughout the model. And we have several MOEs here in our list. And why this is important, maybe I can show some code.
Yeah. So if we grab for one of the error messages for the TorchWare, we see that it's like here. This is the almost
expert.
Expert. And you see also that if you scroll through the stack trace, you will find that it's somewhere in the forward of a module. And if you would go there in the modeling Olmo E, you would find that that is in the mixture of expert MLP, right?
Yeah, exactly. So let's maybe take a look at the actual code in transformers directly. So this is where so here we are in transformers models, and then you were looking at Olmo E, which is evidently it's an MOE. And here, MOE here. And if you go into modeling, you will find this is the MLP, and this is the MLP, just the MLP, but there will be an MOE. Usually there's an MOE layer. One second.
So it should be around line 598.
Oh, thank you very much. Good point.
The power of
yeah.
stack traces.
Let's see. Or maybe we can just
almost 600.
So, almost 600. Yeah, here.
Yeah, there it was.
Yeah, here. Okay, sparse MOE block. This is it. Because they have an MLP. Oh, here. These are experts. So the MLP is the module list that lists experts. And these experts basically are picked. So not all of them are active. And that's the whole point of MOEs. There are some layers before that decide where to direct each token. And so each token gets routed to a subset of the experts. And to choose the experts, we basically do this where, and then this will mean that in the index here, we have data dependency. Because we select something and then we use that something as a way to index into the layers. And so this is basically it's something that we can not know in advance while we trace through the model. And that's the whole point. So it's not pertaining to metadata or to ops. It's actually calling into different layers according to what the data is actually. So that's the whole point of data dependency.
Yeah, and one thing to note here is that, well, yeah, this now is data dependent shape, but it's not, the control flow doesn't vary because you have you don't have an if there, like if there's nothing to compute, or you don't like dynamically select some of the experts, but you have here your loop over all the experts.
Yeah.
But these days, like, people do even more wild things, and then there's distributed across experts, so it becomes non-trivial. And also, even if Thunder could do it easily, one thing we want to do sometimes is to run the model through CUDA graphs. And there you also hit this problem where CUDA graphs, one of the conditions is that all the inputs have the same address. And so if you change like the locations where expert, or the size of the tensors that are sent to each expert, then you're in trouble.
Yeah, exactly. So that's the additional constraint that CUDA graphs have. And they rely on tensor input and output tensors and intermediates that are all pre-allocated and needs to stay at the same spot. And this is the other MOE, one of the popular ones. DeepSeek P3 is an MOE as well. And here we see the loop over experts, and similar patterns here.
Yeah, you even have this if token indices null is greater than 0. So you have this, and there's
further
the
data dependent,
the data dependent control flow, right?
Yeah, exactly. And then we noticed that Llama 4 doesn't have a strongly data dependent path here. Llama 4.
Doesn't look like it if it's written this way, right? But if they say like 16 of 109 billion parameter model is 16 billion of them are active,
Yeah.
That means yeah, something.
Yeah, it doesn't look like from looking at it, but there is a trick, which is this kernel forward from hub. Probably that's where they embedded some dependency there. I don't know.
Yeah.
Anyway, mysterious models, but the point is that we have ideas on how to manage them with Thunder. So that's will probably be some focus in the future to do something with the MOE, either by ignoring what happens in the MOE and disregarding it and just treating it as black boxes, or by saying, okay, we have a special kernel there. And you actually found a very interesting paper that you sent on.
Yeah.
What is it? Let's see if I can bring it up. And whoever wants to read it, it's a good read for the weekend. Let me just share. So this one, that's Flash DMOE, and it's fast distributed MOE in a single kernel. And one of the interesting things here is that people are starting to get creative with the primitives that they use and the way they structure the code in the kernel. So they starting to use certain blocks to be schedulers, and to they call them operating system blocks, to perform administrative tasks and to schedule the work of other CUDA blocks to do stuff, and so that they can do a completely asynchronous scheduling of what's going on, so they don't have stragglers and so on. So that's very, very interesting. I still have to finish reading this paper, but I think it's one of the papers that you need to like sip a spritz and chill, let it go with the flow. But we'll see. It's very interesting and relevant for us because we don't want, like, if we could treat an MOE attention op as a single op, and then we just leave it to the kernel to do whatever it needs to do, that would be super awesome. So yeah, that's it. So I guess that's it for today. All right, so you will see some of these things landing, and also the CI populating with coverage metrics, and yeah, we go from there.
Yeah.
All right. Thank you, Thomas. Have a great weekend.
Yeah, thanks, Luca. You too, and everyone else too, of course.
Bye-bye.
See you.